Hello everyone, today we will study partial derivatives. First of all, let me introduce what is a partial derivative. Let f of sy be a two-variable function. Then the graph of the function is a surface. The graph of the function g equal to f of sy is a surface in R3. R3 represents a three-dimensional space. Usually R2 represents SY plane. R3 represents the three-dimensional space. Assume the surface is smoothed. Assume the surface is smooth at sy equal to AB. Assume the surface smoothed. The partial derivative f sub x of AB represent the rate of change in passive x direction at point AB, and the partial derivative f sub y of AB represent the rate of change in passive y direction at point AB. First of all, let me show you a picture. What does it mean, the rate of change in passive x direction and passive y direction? Let me first of all show you the picture. It will make more sense to you. So, the graph g equal to f of x is a smooth surface. Let me first of all draw a smooth surface. It's an arbitrary surface. Let me draw arbitrary smooth surface first. In R3, let's call this x-axis, y-axis, z-axis. Let me draw arbitrary smooth surface. Assume this surface is g equal to f of sy. Assume this is the surface here. And assume point AB somewhere here. This is point AB. That means x coordinate is A, y coordinate is B. So that's point AB. X coordinate is A, y coordinate is B in the SY plane. What does it mean? Passive x direction. Passive x direction. This is passive x direction. Passing through point AB in passive x direction looks like this. passing through point AB. That's the passive x direction. That's the passive x direction passing through point AB. So that's the passive x direction at point AB. In this direction, we can see that y is the same everywhere. Y is the same everywhere. Since y is the same everywhere, we can fix y equal to b. If I fixed y equal to b, then there's a cross section. If I fix y equal to b, then there's a cross section at y equal to b. Let me draw the cross section at y equal to b. So we can see that in the cross section y equal to b, intersection between the surface and the cross section is a curve. Intersection between the surface and the cross section is a curve. AB is here, so f of AB is somewhere on the line. This is f of AB. Since the partial derivative f sub x of AB represents the rate of change in passive x direction at point AB, it represents the slope of tangent line to the curve. It represents the slope of tangent line to the curve at the point f of AB. It represents slope of tangent line to the curve at point f of AB in passive x direction. How do we find the slope of tangent line? How do we find slope of tangent line at one point? And in general, we cannot find slope of tangent line at one point. In order to find slope of tangent line at one point, we must pick a point that's very, very close to this point. So next, let's pick a point very, very close to this point in passive x direction. Say somewhere here. Let's pick a point very, very close to this point in passive x direction. Assume the distance between 2 points is h. Assume the distance between 2 points is h. So in the cross section, since y fixed to be b, if the distance between 2 points is h, that means the difference of the s coordinate must be h. So the coordinate for this point is a plus h comma b. Since in the cross section y equal to b, y is fixed. If the distance between 2 points is h, that means the difference between s coordinate must be h. So if this point here is a plus h comma b, then the value on the curve must be f of a plus h comma b. The value on the curve must be f of a plus h comma b. That's the value on the curve. Then passing through 2 points, we can find the slope of secant line. Passing through these 2 points, we can find the slope of secant line. Slope of secant line. Slope of a line passing through 2 points is always the rise over the long. Slope of a line passing through 2 points is always rise over long. Here, the rise is the difference between the z values. Rise is the difference between the z values. To find the rise, we take the final z value minus the initial z value. So take the final z value minus initial z value. That's the rise. I get a plus h, f of a plus h comma b minus f of a comma b. Use the final z value minus initial z value. Same as y2 minus y1. Here we use z2 minus z1. Let's call this point z2, this point z1. Over long. Long is the distance between these 2 points. Rise over long. Rise is the distance of the z values. The long is the distance between these 2 points. So distance between these 2 points is h. That's the long. So this is the slope of secant line. This is the slope of secant line passing through these 2 points. But this this slope is not exactly the same as the slope of tangent line. This slope is not exactly the same as the slope of tangent line. In order to find slope of tangent line, we must make the distance h to be very, very small. In order to find the slope of tangent line, we must make distance h to be very, very small. So I take limit as h goes to 0. If h goes to 0, then these 2 points will be very, very close, and eventually we'll find the slope of tangent line at this point. So when h goes to 0, I find the slope of tangent line at this point. Since this expression represents the slope of the line tangent to the curve at point AB, it also represents the rate of change in positive x direction at point AB. So the partial derivative f sub x of AB can be written as this expression: limit h goes to 0, f of a plus h comma b minus f of a comma b over h. And since a and b represent a and b could be any x and y values, this expression can be rewritten as f sub x of sy equal to the limit h goes to 0, f of x plus h comma y minus f of s comma y over h. And this is the definition of partial derivative. This expression is the definition of partial derivative. Next, let's try to find a formula for the other partial derivative, f sub y of ab. The procedure is very, very similar. F sub y of AB represents a rate of change in positive y direction at point AB. So let me first of all draw a similar surface. We can use the same surface to derive f sub y of AB. Let me draw the same surface over. This is the x-axis, this is the y-axis, this is the z-axis. And this surface represents a graph z equal to f of sy. And assume AB is a point in the sy plane. Assume AB is somewhere here. That's an A coordinate, that's the B coordinate. Point AB is somewhere here. This direction is called the positive y direction. This direction is called the positive y direction. F sub y of AB represents a rate of change in positive y direction passing through AB. So at point AB, this is the positive y direction. At point AB, this is the positive y direction. In this direction, x is the same everywhere. In this direction, x is the same everywhere. Since x is the same everywhere, we can fix x to be A. If I fix x to be A, I can draw a cross section at s equal to A. Since I fix x equal to A, I can draw a cross section at s equal to A. That's a cross section at s equal to A. That's the cross section. And we can see that intersection between the cross section s equal to a and the surface is a curve. The intersection between the cross section s equal to a and the surface g equal to f of sy is a curve here. Since AB is here, we have f of AB on the curve somewhere here. This is point f of AB. This is f of AB on the curve. Since f sub y of AB represents the rate of change in the positive y direction, it's the same as the slope of the line tangent to the curve at point AB in positive y direction. It's the same as the line tangent to the curve at point AB in positive y direction, the same as the slope of this line. The same of the slope of tangent line, the same as the slope of the line tangent to the curve at point AB in positive y direction. Now, how do we find the slope of tangent line? Again, we can't find the slope of the line in one point using one point. We must find a point, a very close point in positive y direction. We find a very close point in positive y direction. Say somewhere here. Assume the distance between 2 points is h. Assume the distance between 2 points is h. Then, in this direction, in positive y direction, x is fixed. X is fixed. So if the distance between 2 points is h, that means the b coordinate must be changed by h. Since in positive y direction, x is fixed to be a. If the distance between 2 points is h, then the y coordinate must be changed by h. So this point will be f of a comma b plus h. Next, passing through 2 points, we can try to find the slope of secant line. Slope of secant line is raised over long. Slope of a line passing through 2 points is always rise over long. It's always rise over long. The rise is the change of the z value. The rise is the change of the z value. We use final minus initial, z2 minus z1. We use final minus initial, z2 minus z1. F of a comma b plus h minus f of ab over long. Long is the distance between these 2 points. Long is the distance between these 2 points, which is h. Now, in order to find the slope of tangent line at this point, we must take a limit. We must take a limit as the gap between these 2 points becomes very small. Take a limit. If the gap becomes very small, h must be very close to 0. If h gets very close to 0, we find the slope of tangent line at this point. So when h goes to 0, we have f of a comma b plus h minus f of ab over h. So this expression, it represents the slope of the line tangent to the curve at point AB in positive y direction. So it also represents the rate of change in positive y direction at point AB, which is the partial derivative f sub y of AB again, since a and b represent any x and y value, since a and b could be any x and y value, then this expression can be rewritten as f sub y of s comma y equal to the limit h equals to 0, f of s comma y plus h minus f of xy over h. I substitute x and y for a and b. And that's the definition of partial derivatives. So keep these two formulas in mind. F sub x of sy equal to the limit h goes to 0, f of s plus h comma y minus f of xy over h. F sub y of xy equal to the limit h goes to 0, f of s comma y plus h minus f of sy over h. So they are called the definition of partial derivatives. Keep it in mind. They are called the definition of partial derivatives. Keep it in mind. Next, let's look at an example about the computation of the partial derivatives. Let f of xy equal to 4 minus x squared minus 2y squared. Find f sub x of 1 comma 1 and f sub y of 1 comma 1. So let's first of all compute f sub x. F sub x of sy. Use the definition of partial derivative. Let equal to the limit as h approaches to 0, f of s plus h comma y minus f of sy over h. Limit h approaches to 0. F of x plus h comma y means I substitute x plus h for x and substitute y for y. I have 4 minus x plus h squared minus 2y squared minus f of sy. F of sy is the function itself. Minus 4 minus x squared minus 2y squared over h. Next, we simplify. Keep limit the same. 4 minus x plus h squared is x squared plus 2xh plus h squared minus 2y squared minus 4 minus x squared minus 2y squared over h. Next, limit h approaches to 0. Number 4 stays the same. Distribute. We have distribute negative sign. We have negative x squared minus 2xh minus h squared minus 2y squared. Distribute negative sign. We have negative 4 plus x squared plus 2y squared over h. Then we combine like terms. Positive 4 and negative 4 can cancel. Negative x squared and positive x squared can cancel. Negative 2y squared and positive 2y squared can cancel. What's left is limit h approaches to 0, negative 2sh minus h squared over h. Then on the numerator, I can factor h out. I have h times negative 2x minus h over h. Then cancel h from top and bottom. We have limit h approaches to 0, negative 2x minus h. Then I substitute 0 for h. I get negative 2x. So f sub x of xy equal to negative 2x. Then in order to find f sub x of 1 comma 1, I substitute 1 for x and substitute 1 for y. I have negative 2 times 1, which is negative 2. So f sub x of 1 comma 1 is negative 2. Next, let's compute f sub y. F sub y of f comma y, use definition, equal to limit h approach to 0, f of x comma y plus h minus f of x comma y over h. So limit h approach to 0. For f of x comma y plus h, I substitute x for x and substitute y plus h for y. I have 4 minus x squared minus 2 times y plus h squared. I substitute x for x and substitute y plus h for y. Minus f of sy. F of sy is the function itself. 4 minus x squared minus 2y squared over h. Then we simplify. Limit h approach to 0. 4 minus x squared minus 2 times y plus h squared. Y plus h squared can be rewrite as y squared plus 2yh plus h squared minus 4 minus x squared minus 2y squared over h. Then we have limit h approach to 0. 4 minus x squared. Distribute negative 2 into the parentheses. I have negative 2y squared minus 4yh minus 2h squared. Distribute negative sign. I have negative 4 plus x squared plus 2y squared over h. Next, we combine like terms. Positive 4 and negative 4 can cancel. Negative x squared and positive x squared can cancel. Negative 2y squared and positive 2y squared can cancel. What's left is negative 4yh minus 2h squared over h. Then we can factor h out. If I factor h out, well, I have negative 4y minus 2h over h. Cancel h. We have limit h approach to 0, negative 4y minus 2h. Then I substitute 0 for h. Then I substitute 0 for h. I have negative 4y. So f sub y of xy equal to negative 4y. So f sub y of 1 comma 1. We substitute 1 for x, substitute 1 for y. We have negative 4 times 1 equal to negative 4. Therefore, we have f sub x of 1 comma 1 equal to negative 2 and f sub y of 1 comma 1 equal to negative 4. This computation looks okay, but is there any easier way? In order to find a simpler way to compute the partial derivatives, let's first of all go back to the definition of partial derivative first. When we compute f sub s of ab, we first of all fix y equal to b. Then we compute the slope of the line tangent to the curve in the cross section at point AB. Now, let's reconsider this process over. In function f of sy, if we fix y equal to b and keep x as a variable, then f of sy can be rewritten as f of s comma b. Since we treat y as a constant b, f of sy can be rewritten as f of sb. Then we can see that this function f here is a single variable function. The only variable here is x. This f is a single variable function. The only variable in the function is x. Then, since this function f now is a single variable function with variable x, I can let g of x, I can call this function g of x. Let g of x equal to f of sb. Then, g of a will be f of a comma b. And g of a plus h, for g of a plus h, I plug in a plus h for each x. I have f of a plus h comma b. I plug in a plus h for x. Now, let's look at f sub s of ab. F sub s of ab is the limit as h goes to 0, f of a plus h comma b minus f of a comma b over h. Since g of a is f of a comma b, g of a plus h is f of a plus h comma b, then it can be rewritten as, this expression can be rewritten as limit as h goes to 0, g of a plus h minus g of a over h. And this is the definition of derivative for single variable functions. This is the definition of derivative for single variable functions. This is g prime of a. This is g prime of a. Since a could be any x values, then f sub x of s comma b equal to g prime of x. Since a could be any s value, I can replace letter a with letter x. And also, since b could be any y value, then f sub x of, I can replace b with y. So f sub s of sy equal to g prime of x. Since b could be any y value, so I can replace letter b with letter y. This expression means, in order to find the partial derivative f sub s of sy, we treat y as a constant and take derivative with respect to x. So, to find f sub x of sy, we treat y as a constant and take the derivative with respect to x. And similarly, to find f sub y of sy, we treat s as constant and take the derivative with respect to y. Those are the rules for finding partial derivatives. With this new rule, finding partial derivative will be much easier. Let's redo the previous example using the new technique. F of sy equal to 4 minus s squared minus 2y squared. If we find f sub x of x and y, that means we take partial derivative with respect to x. We treat y as a constant. So 4 is a constant, 2y squared is a constant. When we take derivative, they both become 0. Then we take derivative for negative x squared with respect to x. I have negative 2x. Then if I plug in 1 and 1, f sub x of 1 comma 1, I substitute 1 for x. I have negative 2 times 1 equal to negative 2. Then next, for f sub y of x and y, we take partial derivative with respect to x. We take partial derivative with respect to y. We treat s as constant. When we take derivative, 4 becomes 0, s squared becomes 0, and negative 2y squared becomes negative 4y. Then substitute f sub y of 1 comma 1 is negative 4 times 1 equal to negative 4. Using the new technique, partial derivative will be much easier. Next, let's practice some computation for partial derivatives. First of all, let me introduce some notation for partial derivatives. We already see this notation, f sub x of a, b. Sometimes we just write f sub x. Sometimes we may write delta f over delta x, or delta over delta x of f of x, f of sy. They all mean partial derivatives. And similarly, f sub y of a, b. Sometimes we write it as f sub y, or we write delta f over delta y, or we may write delta over delta y, f of x, y. They all mean the same. First row means the partial derivative with respect to x. Second row means the partial derivative with respect to y. Let's look at some examples. Do some simpler one first. For each of the following functions, find its partial derivative. First example, f of sy equal to 3x minus x squared y squared, x squared y squared, minus 2s cubed y. When we are finding partial derivatives, we must find f sub x and f sub y. Let's find f sub x first. F sub x of sy. When we are finding f sub x, we treat y as constant. Take derivative with respect to x. Treat y as constant. So when I take derivative for 3x, I get 3. When I take derivative for negative x squared y squared, we treat y as constant. Since y squared here is a constant multiple, we leave it the same. Take derivative for x squared. I have negative 2x y squared. For the third term, since I treat y as a constant, this y here is a constant multiple, it stays the same. We take derivative for 2x cubed, which is negative 6x squared. Y stays the same. Then for f sub y of sy, we take derivative with respect to y. That means we treat x as constant. Treat x as constant. Take derivative with respect to y. So first term is 3x. Since I treat x is constant, the entire term is a constant. Derivative of 3x is 0. For the second term, since I treat x squared as a constant multiple stays the same. So when I take derivative for y squared, I have 2y. I have negative 2x squared y. That's the second term. For the third term, I treat 2x cubed as constant. Take derivative for y. Derivative of y is 1. So I have negative 2x cubed. That's the partial derivative of the function. Next, f of sy equal to x times e x squared y. This function has two variables, x and y. So we must find f sub x and f sub y. Let's find f sub x first. For f sub x, I take partial derivative with respect to x. I treat y as constant. So when I take derivative with respect to x, and that's a function of x, that's another function of x, we need to use product rule. So do product rule. The derivative of the first times the second plus the first times derivative of the second. For exponential function, its derivative stays the same. Then by chain rule, we multiply by the derivative of exponent. For derivative of exponent, we treat y as constant. Take derivative for x squared. I have 2xy. Y is a constant multiple, it stays the same. Derivative of x squared is 2x. Then next we find f sub y of sy. For f sub y of sy, we treat x as constant. So that's a constant multiple. When we take derivative with respect to y, it stays the same. Take derivative for an exponential function. I have e x squared times y. Then by chain rule, I multiply by the derivative of the exponent. When I take derivative for x squared y, I treat x squared as constant. I take derivative for y. Derivative of y is 1. 1 times x squared is x squared. That's the partial derivative for f sub y. Next, f of x, y, z equal to x, y plus y, z squared plus xz. This is a function with 3 variables. The way to find partial derivative is very, very similar. To find f sub x, we treat yz as constant. To find f sub y, we treat xz as constant. Take derivative with respect to y. And to find f sub z, we treat sy as constant, then take derivative with respect to z. Let's do each one individually. First one, f sub x. We treat yz as constant. Take derivative with respect to x. Since y is constant, derivative of sy become y. Second term, since yz is constant, they are both constant, the entire term is constant, its derivative is 0. For the third term, xz, since we treat z as constant, take derivative for xz, we get z. That's f sub x. Now for f sub y, we treat xz as constant. Take derivative with respect to y. So first term, we treat x as constant. Take derivative with respect to y. I get x. Second term, I treat z as constant. Take derivative with respect to y. I get z squared. Third term, since I treat both x and z as constant, the entire term becomes 0. Then for f sub z, we treat both x and y as constant. Take derivative with respect to z. First term, both x and y are constant. The entire term is constant, so its derivative is 0. Second term, since I treat y as constant, I take derivative for z squared. I bring 2 to the front, I get 2yz. Third term, I take derivative with respect to z. I treat s as constant, so derivative of xz become x. That's the partial derivative. Number 4. F of x, y, z equal to z sine of xy squared plus 2z. If a function has 3 variables which have 3 partial derivatives, f sub x, f sub y, f sub z. If a function has 3 variables which have 3 partial derivatives, do each one individually. First one, for f sub x, we treat yz as constant, take derivative with respect to x. So z is a constant multiple, it stays the same. Take derivative for sine, I get negative cosine, I get positive cosine. Then use chain rule, the inside function stays the same, then times the derivative of the inside function with respect to x. So we treat y squared as constant, derivative of xy squared become y squared, and we treat z as constant, derivative of 2z becomes 0. Then f sub y, we take derivative with respect to y, treat xz as constant, treat sz as constant. So this z is a constant multiple, stays the same. Take derivative for sine, I get cosine. Inside stays the same, the inside stays the same. Then multiply by the derivative of the inside. By chain rule, we multiply by the derivative of the inside. With respect to y, we treat xz as constant. When I take derivative with respect to y, x times y squared becomes 2xy. I bring 2 to the front. Then last term, since I treat z as constant, 2z is also a constant. The entire term becomes 0. Last one, f sub z. For f sub z, I treat both s and y as constant and take derivative with respect to z. With respect to z, there are 2 functions of z. There are 2 functions of z here. We need to use product rule. Use product rule. Derivative of the first times the second plus the first times derivative of the second. When we take derivative for sine function, it becomes cosine. The inside stays the same, s squared xy squared plus 2z. Then by chain rule, we need to multiply by the derivative of the inside with respect to z. With respect to z means I treat s and y as constant, so the entire term is constant, its derivative is 0. For the second term, if I take derivative with respect to z, I get positive 2. That's the partial derivatives. Next, we'll study implicit differentiation with partial derivatives. Before we involve partial derivative, let's review some old problems we learned in our first semester calculus class. Find dy over dx. First problem, s cubed plus 2y squared equal to 2x. That's a problem we learned in our first semester calculus class. In order to find dy over dx, we treat y as a function of x. In order to find f of x, in order to find dy over dx, we treat y as a function of x. Then we take derivative for each term individually. S cubed is 3x squared. 2y squared is 4y, but multiplied by dy over dx by chain rule. Since y is a function of x, multiplied by dy over dx by chain rule. Then take derivative for 2x, we get 2. Take derivative for each term first. Take derivative for each term first. Then we solve an equation for dy over dx. Solve an equation for dy over dx. Dy over dx equal to 2 minus 3x squared over 4y. Next, let's try a harder example. X squared times y cubed plus 4y squared equal to ax squared. We take derivative for each term individually. When we take derivative for the first term, we have x squared times y cubed. Since we treat y as a function of x, we need to use product rule for x squared and y cubed. So we use product rule. We have derivative of the first times the second plus the first times derivative of the second. And every time when you take derivative for a function of y, you need to multiply the result by dy over dx. That's the first term. Next, take derivative for the second term. When we take derivative for 4y squared, we get ay. Remember, every time when we take derivative for a function of y, you need to multiply the result by dy over dx. Then the last term, when we take derivative for ax, when we take derivative for ax squared, we have 16x. Then we solve an equation for dy over dx. Next, we solve an equation for dy over dx. S squared times 3y squared can be rewritten as 3x squared y squared. Dy over dx stays the same. Plus ay dy over dx equal to 16x. Move this term over, it becomes negative 2sy cubed. Then we can factor dy over dx out. We have 3x squared y squared plus ay times dy over dx. Factor dy over dx out equal to 16x minus 2xy cubed. Then divide both sides by divide both sides by 3x squared y squared plus ay. We have 16x minus 2xy cubed over 3x squared y squared plus ay. That's the implicit differentiation. So remember the steps. First step, you take derivative for each term individually. Then solve an equation for dy over dx. Take derivative for each term individually. Then solve an equation for dy over dx. Next, let's look at some example that involves partial derivative. Find delta z over delta x and delta z over delta y. First example, yz minus ln of z equal to x plus y. So since we are looking for delta z over delta x, delta z over delta y, that means we must treat z as a function of x and y. We must treat z as a function of x and y. Let's first of all find delta z over delta x. If we try to find delta z over delta x, we treat x as a variable, treat y as a constant, and z is a function of x. We treat x as a variable, treat y as constant, treat z as a function of x. So first term, we treat y as constant, take derivative for z. Derivative of z is 1, so we get y times derivative of z is 1. But every time when you take derivative for a function of z, you multiply by delta z over delta x. That's the first term. Next term, take derivative for ln of z, we get 1 over z. Every time when you take derivative for a function of z, multiply by delta z over delta x. On the other side, take derivative for x, we get 1. Take derivative for y. Since we treat y as constant, derivative of y is 0. Then solve the equation for delta z over delta x. So I can factor delta z over delta x out. I get 1y minus 1 over z, y minus 1 over z times delta z over delta x equal to 1. Then delta z over delta x equal to 1 over y minus 1 over z. Divide both sides by y minus 1 over z. We get delta z over delta x by itself. Next, we'll try to find delta z over delta y. For delta z over delta y, we treat x as constant, treat y as a variable, treat z as a function of y. Every time when we take derivative for a function of z, multiply by delta z over delta y. So take derivative from the first term. First term contains y and z. Since z is a function of y, we need to use product rule from the first term. Since z is a function of y, we need to use product rule from the first term. Derivative of the first times the second plus the first times derivative of the second. Derivative of z is 1. When we take derivative for z, since z is a function of y, by chain rule, you need to multiply by delta z over delta y. That's derivative of the first term. Second term, take derivative for the second term. For ln of z, the derivative is 1 over z. Then by chain rule, since z is a function of y, I need to multiply by delta z over delta y. On the other side, equal to x plus y. Take derivative for x. Since I treat x as constant, derivative of x is 0. Then take derivative for y. Derivative of y is 1. Then I need to solve the equation for delta z over delta y. Then solve the equation for delta z over delta y. I first of all multiply y and 1 together. I get y times delta z over delta y minus 1 over z times delta z over delta y. Move the first term over. I get 1 minus z. Then factor delta z over delta y out. I get y minus 1 over z times delta z over delta y equal to 1 minus z. Then to get delta z over delta y by itself, I divide both sides by y minus 1 over z. So I get 1 minus z over y minus 1 over z. That's the partial derivative. Next, s cubed plus y squared z equal to xz. Again, in order to find delta z over delta x and delta z over delta y, we must treat z as a function of x and y. We must treat z as a function of x and y. Let's find delta z over delta x first. So take derivative for each term. We treat x as a variable, y as a constant, and we treat z as a function of x. Take derivative for each term individually. Take derivative from the first term. S cubed becomes 3x squared. Take derivative from the second term. Since I treat y as constant, I only take derivative for z. Y squared is a constant multiple. Take derivative for z, I get y squared. Then every time when I take derivative for z, I need to multiply by delta z over delta x by chain rule. Every time when you take derivative for a function of z, you multiply by delta z over delta x by chain rule equal to x times z. When we see x times z is a function of x, we need to use product rule. So use product rule. Derivative of the first times the second plus the first times derivative of the second. Derivative of z is 1. And every time when we take derivative for z, multiply by delta z over delta x by chain rule. Then we try to solve the equation for delta z over delta x. Let's move this term x times 1 times delta z over delta x. Move this term to the left side. And move 3x squared to the right side. Y squared delta z over delta x minus x times delta z over delta x equal to 1 times z is z. When I move 3s over, it becomes negative 3x squared. Then I can factor pull out delta z over delta x. I have y squared minus x times delta z over delta x equal to z minus 3x squared. Then solve an equation for delta z over delta x. Delta z over delta x is z minus 3x squared over y squared minus x. It's delta z over delta x. Next, we try to find delta z over delta y. For delta z over delta y, we treat x as a constant, treat y as a variable, and treat z as a function of y. So take derivative for each term individually. For the first term, since x is constant, its derivative is 0. For the second term, since z is a function of y, we need product rule. Derivative of the first times the second plus the first times derivative of the second. Derivative of z is 1. Then times dz over dy. Every time when we take derivative for a function of z, multiplied by dz over dy. Next, take derivative for xz. Since s is constant, derivative of xz become x. Then remember, multiplied by delta z over delta y. Every time when we take derivative for a function of z, multiplied by delta z over delta y. Then solve an equation for delta z over delta y. Try to move this term over. Y squared times delta z over delta y minus x times delta z over delta y. And move 2yz to the other side, to the right side. Then factor delta z over delta z over delta y out. Factor delta z over delta y out. We have y squared minus x equal times delta z over delta y equal to negative 2yz. So delta z over delta y equal to negative 2yz over y squared minus x. That's delta z over delta y. Next example. Sine of sy plus cosine of yz equal to tangent of xz. When we try to find delta z over delta x and delta z over delta y, we treat z as a function of x and y. Let's find delta z over delta x first. When we try to find delta z over delta x, we treat x as a variable, treat y as a constant, treat z as a function of x. Then take derivative for each term individually. Let's take derivative for the first term. Derivative of sine of sy is cosine of sy. Then by chain rule times the derivative of the inside function. For the inside function, I treat y as a constant. So derivative of sy is y. Second term, I take derivative for cosine of yz. Derivative of cosine is negative sine of yz. Then take derivative for the inside function. For the inside function, I treat y as a constant. So take derivative for z. I have delta z over delta x. The third term, when I take derivative for tangent of xz, I use chain rule. I get secant square of xz. Then times the derivative of the inside function. For the inside function, x times z. X is a function of x. Z is also a function of x. I need to use product rule. So product rule, derivative of the first times the second plus the first times derivative of the second. Derivative of z is delta z over delta x. Then solve an equation for delta z over delta x. let me simplify each term first. First term can be rewritten as y times cosine xy. Second term can be rewritten as y times sine yz times delta z over delta x. On the other side, I distribute secant square into the parentheses. Distribute secant square of xz into the parentheses. I have z times secant square xz plus x times secant square xz times delta z over delta x. Then I try to move the last term to the left side, move the first term to the right side. I have negative y sine yz delta z over delta x minus x secant square xz delta z over delta x. Move first term to the right side. I have negative y cosine xy minus plus z secant square xz. Then on the left side, I can factor delta z over delta x out. Put it on the back. I have negative y sine yz minus x secant xz equal to negative y cosine xy plus z times secant square xz. Then I can divide both sides by this. Delta z over delta x is negative y cosine xy plus z times secant square xz over negative y sine yz minus x secant square xz. Next, let's find delta z over delta y. For delta z over delta y, we treat x as a constant, treat y as a variable, treat z as a function of y. Then take derivative for each term individually. When we take derivative for sine sy, I have cosine sy times the derivative for the inside. Inside is sy. When I take derivative with respect to y, I get x. Second term, take derivative for cosine of yz, I get negative sine of yz. Since I treat z as a function of y, I need to use product rule for the inside. So use product rule for the inside. Derivative of the first times the second plus the first times derivative of the second. Every time when I take derivative for z, I multiply by delta z over delta y. On the other side, tangent xz, I take derivative for tangent xz, I have secant square xz, then times the derivative of xz. Since I treat x as a constant, treat z as a function of y, I have x times delta z over delta y. Then I try to solve the equation for delta z over delta y. Let me rewrite the equation first. I have x cosine sy, then distribute sine sy into the parentheses. I have negative z sine yz minus y sine yz delta z delta y equal to x secant square xz delta z delta y. Then we try to solve the equation for delta z over delta y. Let me move the last term to the left side and move the first two terms to the right side. I have y, negative y sine yz delta z over delta y minus x secant square xz times delta z over delta y equal to negative x cosine xy plus z sine yz. Then I can factor pull out delta z delta y. I have negative y sine of yz minus x times secant square of xz equal to negative x cosine sy plus z sine of yz. Then solve for delta z over delta y. I divide both sides by this. I have negative x cosine sy plus z sine yz over negative y times sine yz minus x times secant square xz. That's delta y, delta z over delta y. Next, let me introduce second order partial derivatives. What's second order partial derivatives? When we take partial derivative twice for any variable, what we get is called the second order partial derivative. Let me show you an example. Suppose f has two variables, x and y. When we take partial derivative with respect to x and y, we have two partial derivatives, f sub x of sy and f sub y of sy. F sub x, f sub y, they are both functions of x and y. Then, when I take a partial derivative one more time, I have f sub x with respect to x, f sub x with respect to y, f sub y with respect to x, f sub y with respect to y. They are called the second order partial derivative of f of x. So f sub x of x can be rewritten as fxx. F sub x sub y can be rewritten as fxy. And this one can be rewritten as fyx. Last one can be rewritten as fyy. They are called the second order partial derivative. Let me introduce some notation here. F sub xx is the same as fxx. That means we take a partial derivative with respect to x, then take another partial derivative with respect to x. It can be rewritten as delta over delta x times delta f over delta x. Means we take a partial derivative with respect to x, then take another partial derivative with respect to x. That can be rewritten as delta square f over delta x square. And similarly, fxy can be rewritten as fxy equal to delta over delta y, delta f over delta x equal to delta square f over delta x, delta y delta x over delta y delta x. Next one, fyx, and that's f sub y of sub x. That's delta x times delta f, delta over delta x times of delta f over delta y equal to delta square f over delta x delta y. And f sub yy equal to f sub y of y equal to delta over delta y, delta f over delta y. equal to delta square f over delta y square. This notation, be very, very careful for this notation here. Delta square f, delta y, delta x, we must take partial derivative backward. Do partial derivative with respect to x first, then with respect to y. Read it backward. Take partial derivative with respect to y first, then with respect to x. For this notation, you must read operation backward. And for this notation, read it backward. Read it forward. Do partial derivative with respect to x first, then partial derivative with respect to y. For this notation, read the partial derivative forward. For this notation, read the partial derivative backward. They are called the second order partial derivatives. Then, if we take partial derivative multiple more than 2 times, those are called higher order partial derivatives. If we take partial derivative more than 2 times, those are called higher order partial derivatives. For example, if I take a partial derivative with respect to x, y, x, z, that means I take a partial derivative with respect to x first, then take partial derivative with respect to y, then again take partial derivative with respect to x, then with respect to z. It can be rewritten as delta to the power 4 of f over delta z, delta x, delta y, delta x. We must write the operation backward. Delta x, delta y, delta x, delta z. In this symbol, we must write the partial derivative backward. Take operation backward. For this notation, take operation forward. X, y, x, z. X, y, x, z. Next, let's practice some problems about second order partial derivatives. Look at this example. Let f of sy equal to 3xy squared minus 2y plus 5x squared y squared. Find its second order partial derivatives. And determine their values at -1, 2. So let's find the second order partial derivative first. Before we find second order partial derivative, we must find the first order partial derivative first. F sub x. If I take partial derivative with respect to x, I have 3y squared. I treat y as constant, that becomes 0. I treat y as constant, I have 10x y squared. Then we find f sub y. Take partial derivative with respect to y, that means I treat s as constant. I have 6xy minus 2 plus 10x squared y. Then for f sub xx, take partial derivative with respect to x. In f sub x, take partial derivative with respect to x. I treat the first one as constant. I have 10y squared. Then for f sub xy, f of f sub sy, I take partial derivative with respect to y. We take partial derivative with respect to y. That's 6y. I treat s as constant, so I have 20 sy. Next, for f sub yx, I take partial derivative for f sub y with respect to x. Take partial derivative with respect to x. I treat y as constant. I have 6y. That's a constant. Its derivative is 0. Take partial derivative with respect to x. I have 20 as y. That's fyx. Then fyy. For fyy, we take partial derivative with respect to y. So I treat s as constant. I have 6x. Number 2 is constant. Its derivative becomes 0. Take partial derivative with respect to y. I have 10x squared. Then we evaluate the value at 1, 2. F sub xx of -1, 2. We substitute -1 for x, substitute 2 for y. I get 10 times 2 squared equal to 40. F of sy of f sub sy of -1, 2. I substitute -1 for x, substitute 2 for y. 6 times 2 plus 20 times -1 times 2. That's 12 minus 40. That's -28. For f sub yx of -1, 2. I have 6 times 2 plus 20 times -1 times 2, which is 12 minus 40 equal to -28. Then the last one, fyy. I substitute -1 and 2 for x and y. I have 6 times -1 plus 10 times -1 squared, which is -6 plus 10 equal to 4. Those are the second order partial derivative. Now let's observe. Do we see something interesting here? Observe f sub sy and f sub yx. They look exactly the same. Is this coincident, or is this the true? Is this coincident, or they're always the same? F sub sy and f sub yx, are they always the same, or that's just a coincidence? Let's look at another example, see if that's a coincidence or not. Next example. F of sy equal to s cubed times y minus x times y cubed over x squared plus y squared if sy is not 0, 0 and fsy equal to 0 if xy equal to 0, 0. Determine whether f of sy 0, 0 is the same as f sub yx of 0, 0. Let's try this example. How do we find f sub xy and f sub yx? In order to find the second order partial derivatives, we must compute the first order partial derivatives. So let's find f sub x first. This is a piecewise defined function. So to find f sub x, let's consider two cases. Case 1, if xy is not 0, 0, then f sub x equal to, we can use quotient rule here. Quotient rule, derivative of the top times the bottom minus the top times derivative of the bottom over bottom square. If we simplify, we have 3x to the power 4 y plus 3x squared y cubed minus x squared y cubed minus y to the power of 5. Distribute 2x, we have negative 2x to the power 4y plus 2x squared y cubed over s squared plus y squared squared. Then we try to combine like terms. If I combine like terms, 3x to the power 4y minus 2x to the power 4y will be x to the power 4y. 3x squared y cubed minus s squared y cubed will be 2s squared y cubed plus another 2s squared y cubed will be 4x squared y cubed and minus y to the power 5 over s squared plus y squared squared. That's f sub x if sy is not 0, 0, or if sy is 0. Or if sy is 0. Then we need to use definition of the partial derivative to find f sub x. F sub x of 0, 0 is the limit as h approaches to 0 f of x plus h comma y, both s and y are 0, 0, minus f of xy, both s and y are 0, 0, over h. That can be rewrite as limit as h approaches to 0 f of h comma 0, 0 plus h is h, minus f of 0, 0 over h. For h, f of h0 is not always 0, 0, because h is not 0, h is approaching to 0, s is not 0, h is not 0. So for f of h0, we need to plug in into the first part of the function. Plug in h for x, plug in 0 for y. If I plug in 0 for y, the entire numerator is 0. Denominator is h squared. 0 over h squared is 0. That equal to limit as h approaches to 0, 0 minus f of 0, 0. F of 0, 0 is also 0 over h, which is 0. So f sub x of sy equal to x to the power 4y plus 4x squared y cubed minus y to the power 5 over s squared plus y squared squared if sy is not 0, 0 and equal to 0 if both s and y are 0. That's f sub x. Next, we try to find f sub y. So again, there are two cases. If s and y, they are not both 0, 0, f sub y of sy, we use quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom over bottom square. Then simplify. We have x to the power 5 plus x to the power 3y squared minus 3x to the power 3 y squared minus 3x y to the power 4 minus 2x to the power 3 y squared plus 2xy to the power 4 over x squared plus y squared squared. Next, we combine like terms. We have x to the power 5. Combine like terms. That's negative 2x cubed y squared plus another negative 2. It will be negative 4x cubed y squared. Combine like terms. Combine another like term. I have minus xy to the power 4 over s squared plus y squared squared. That's when sy is not both, they are not both 0. Or if sy, they are both 0. Or if s comma y equal to 0, 0, 0. Then we need to use definition of the partial derivative. F sub y of 0, 0 equal to the limit as h approaches to 0, f of x comma y plus h minus f of xy, f of x comma x plus h. So f of x comma y plus h. Here both s and y are 0. So f of 0 comma 0 plus h minus f of sy. Both s and y are 0 over h. Then we have limit h approach to 0. 0 plus h is h. We have f of 0 comma h minus f of 0, 0 over h. For f of 0, h, we substitute 0 for x, h for y. If I substitute 0 and h into the original function, I get 0. F of 0, 0 is also 0 over h. It turned out to be 0. So f sub y of s to y equals to x to the power 5 minus 4s cubed y squared minus x y to the power 4 over x squared plus y squared to the power 2 if x and y, they are not both 0, 0, and the function f sub y equal to 0 if both x and y are 0. Next, based on f sub x, based on the partial derivative f sub x, I try to find f sub xy at 0, 0. That can be rewritten as f sub x sub y at 0, 0. Using the definition of partial derivative, that can be rewritten as limit as h approaches to 0, f sub x of 0 plus h. So f sub x of 0 comma 0 plus h minus f sub x of 0, 0 over h. Then if I simplify, I have 0 comma h, f sub x of 0 comma h minus f sub x of 0, 0 over h. Limit as h approaches to 0. F sub x of 0 comma h, I plug in 0 for x, plug in h for y. Plug in 0 for x, plug in h for y. I have negative h to the power 5 over h to the power 4 minus f sub x of 0, 0 is 0 over h. That's the limit h approach to 0, negative h over h. So the limit is negative 1. So f sub xy of 0, 0 equal to negative 1. So f sub xy of 0, 0 equal to negative 1. Next, based on f sub y of sy, we try to compute f sub y x at 0, 0. That can be rewritten as f sub y sub x at 0, 0. Again, we use the definition of partial derivative to compute this partial derivative here. Take a limit as h approach to 0, f of 0 plus h comma 0 minus f of f sub y of 0 plus h comma 0 minus f sub y of 0, 0 over h. Simplify, we have limit as h approach to 0, f sub y of h comma 0 minus f sub y of 0, 0 over h. That equal to f sub y of h0 means I plug in h for x, plug in 0 for y. If I plug in h for x, plug in 0 for y, I have h to the power 5 on the top. If I plug in h for x, 0 for y, I have h to the power 4 on the bottom minus f sub y of 0, 0 is 0 over h. If we simplify, we have h over h, which is 1. So f sub yx of 0, 0 equal to 1. Since f sub xy of 0, 0 equal to negative 1 and f sub yx of 0, 0 equal to positive 1, so they are not the same. If f sub xy and f sub yx is not the same at 0, 0, we say fsy is not the same as fyx. So the function fsy is not the same as fyx. If two functions is not the same at any point, then two functions is not the same. We say they are not the same function. So f sub sy is not the same as f sub yx in general. But there's a theorem. It says under one condition, they will be the same. Under one condition, f sub sy will be the same as f sub yx. This theorem is called Clairaut theorem. Clairaut, Clairaut theorem. Clairaut theorem says, suppose f is defined on a disk that contains point A, B. If f sub sy and f sub yx is continuous on D, then f sub xy of AB is the same as f sub yx of AB for all AB belongs to D. Let's clear out theorem. If we look at example that we did earlier, the second order partial derivatives f sub sy, f sub yx, they are both polynomials. Polynomials are continuous everywhere. So by cross theorem, they must be the same. Only other example in which we show that f sub sy is not the same as f sub yx at 0, 0. Let's try to compute the second order partial derivatives. Let's compute f sub xy first. We compute f sub sy based on f sub x. Since f sub x is a piecewise function, when we take derivative with respect to y, we consider two cases. Case 1, if sy is not 0, 0, then if sy is not 0, 0, then we can take partial derivative with respect to y. Use this function, take partial derivative with respect to y. We use quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom. Here is my work in detail. You can pause the video and write down the work. Here is my conclusion. That's my f sub sy. So when sy is not 0, 0, f sub sy of sy equal to this expression here. Now, what if s comma y is 0, 0? If s comma y is 0, 0, then we try to find the partial derivative at 0, 0 using the definition of partial derivatives, which we did earlier. Fsy 0, 0 equal to -1. So if s comma y equal to 0, f sub sy of 0, 0 equal to -1. So f sub sy is a piecewise function. That equal to x to the power 6 plus 9x to the power 4 y squared minus 9y x squared y to the power 4 minus y to the power 6 over x squared plus y squared to the power 3 if sy is not 0, 0 and f sub sy of xy equal to -1 if sy is 0, 0. Then similarly, we can try to compute f sub yx. We compute f sub yx based on f sub y. We compute f sub yx based on f sub y. F sub y, again, is a piecewise defined function that we compute earlier. To compute f sub yx, we need to consider two cases. Case 1, if sy is not 0, 0, then for f sub y of x, we can use quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom over bottom squared. Take derivative with respect to y. Here is my work. I did quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom with respect to y over the bottom square. Then simplify. I get this. That's my work for f sub y of x. You can pause the video and see my work in detail. So when sy is not 0, 0, I have f sub yx equal to this. But what if sy is 0? If sy is 0, 0, then we use the definition of partial derivative to compute f sub yx at 0, 0. And we did this earlier. In this example, we compute earlier f sub yx at 0, 0. That is positive 1. So when sy is 0, 0, f sub yx of 0, 0 is 1. So f sub yx is again a piecewise function equal to x to the power 6 plus 9x to the power 4 y squared minus 9x squared y to the power 4 minus y to the power 6 over x squared plus y squared raised to power 3 if sy is not 0, 0 and equal to positive 1 if sy is 0, 0. Crowd's theorem says if both f sub sy and f sub yx are continuous, then f sub sy equal to f sub yx. Now, is these two functions continuous? Are they continuous at 0, 0? Let's use path test. Let's use path test to take limit. If I take limit along the path s equal to 0 and take limit along the path y equal to 0, I believe we get different limits. You can verify by yourself. If we get the two different limits along two different paths, the limit does not exist. Since the limit does not exist, the function is not continuous at 0, 0. And same thing here. If you take a different path, if you take path along the path s equal to 0 and limit along the path y equal to 0, we also get two different limits. You can verify by yourself. If we get two different limits along two different paths, the limit does not exist. So the limit does not exist at 0, 0. Since the limit does not exist, the function is not continuous at 0, 0. Since both f sub sy and f sub yx, they are not continuous, we can apply Crowd's theorem here. That's not a contradiction. Next, let's use an example to verify Crowd's theorem. Let f of syz equal to yex plus x ln of z. Part A. Verify that f sub xy equal to f sub yx. Part B. Verify that f sub xzz equal to f sub gxz equal to f sub zzx. Let's verify part A first. Part A, f sub sy. We take partial derivative with respect to x first. Take partial derivative with respect to x. I have yex, I treat y as constant, plus ln of z. Then I take partial derivative with respect to y. Take partial derivative with respect to y. I treat s as constant. I get ex. I treat z as constant. That's 0. The derivative is 0. Then I try to verify. I try to find f sub yx. I find f sub y first. For f sub y, I treat x and z as constant. I get e to the power x. Xz is constant. The entire term is a constant. Its derivative is 0. Then we find f sub yx. If we find f sub yx, I take derivative with respect to x. I get the same thing. So they are the same. Clairaut theorem also works for more than 2 variables. It works for 3 or more variables. Part B. Let's compute the first one first. F sub x is yex plus ln of z. Then we do f sub xz. Take partial derivative with respect to z. So we treat sy as constant. That becomes 0. We get 1 over z. 1 over z can be rewrite as z raised to -1. Then I take partial derivative again for another z. F sub xzz. When I take partial derivative, I bring -1 to the front. -1 times z raised to -2. If I simplify, that's -1 over z squared. That's the first one. Let's verify the second one. Fzxz. So I compute f sub z first. F sub z, I take partial derivative with respect to z. So I treat sy as constant. Its derivative is 0. Take partial derivative with respect to z. I have x times 1 over z. That can be rewrite as x times z raised to -1. Then I compute f sub zx. I take a partial derivative with respect to x. I get z raised to -1. Then I do f sub zxz. Take partial derivative with respect to z. I have -1 times z raised to -2. That's, if I simplify, that's -1 over z squared. Then verify the third one. F sub z is x times 1 over z, which is xz raised to -1. The same as here. F sub zz. Take another partial derivative with respect to z. I treat x as constant. I have -x z raised to -2. That can be rewrite as -x z raised to -2. Then f zx. Take partial derivative with respect to x. I have -z squared. No, -z raised to -2, which is -1 over z squared. So they are all the same. Clairaut theorem works for not only for 2 variable functions, it works for multi-variable functions. Next, let's do some exercise about second order partial derivatives. Example, let u of sy equal to e to the power x sine y. Verify that u of xy satisfies Laplace equation. U sub xx plus u sub yy equal to 0. To verify an equation, you simply compute u sub xx, compute u sub yy, then add them up to verify their sum is 0. So let's compute each of them individually. So let's compute u sub x first. Take partial derivative with respect to x. I treat y as a constant. I get ex sine y. Take another partial derivative with respect to x. I treat y as constant. That's ex sine y. Then for u sub yy, I first of all compute u sub y. I take partial derivative with respect to y. I treat x as constant. I have e sub x times negative cosine y. Then for u sub yy, I take partial derivative with respect to y. I treat x as constant. I have ex times negative sine y. That can be rewrite as negative ex sine y. Then we can see that if I add them up, u sub xx plus u sub yy. I have e to the power x sine y plus negative e to the power x sine y. If I add them up, I get 0. Let's verify Laplace equation. Next example, let's verify a width equation. Let u of sy equal to sine of x minus at. Verify that u of x comma t satisfies the width equation. Width equation is d delta square u over delta t square equal to a square times delta square u over delta x square. So to verify the equation, do the same thing. We compute the left side, compute the right side, and to show that they are the same. Let's compute left side first. Left side, we must compute the second order partial derivative with respect to t twice. Let's first of all compute the delta u over delta t. U should be a function of xt instead of sy. U should be a function of xt. Let's compute delta u over delta t. We take partial derivative with respect to t. So derivative of sine is cosine. If I take partial derivative with respect to t, I leave the inside the same, use the chain rule, I got negative a here. Next, I take another partial derivative with respect to t. Delta square u over delta t square is, take derivative for cosine, I have negative sine x minus a t, then use chain rule with respect to t, with chain rule. We take derivative with respect to t, I have another negative a here. So left hand side equal to delta square u over delta t square equal to negative, triple negative is negative, negative a square sine of x minus a t. Now let's compute the right hand side. Compute the partial derivative with respect to x first. If I compute the partial derivative with respect to x, I treat t as constant. Take derivative for sine, I get cosine of x minus at. Derivative of x minus at with respect to x is 1. Take the second order partial derivative with respect to x. Derivative of cosine is negative sine. Then take derivative with respect to x is 1. So the right hand side equal to a squared times delta square u over delta x square, which is a squared times negative sine x minus at. If we simplify, that's negative a squared sine of x minus at. We can see that they are the same. So left hand side equal to the right hand side. That's how we verify our equation.